Hello. Today we're going to talk about Topic 4, Section 15, the Central Limit Theorem. But first, we need to discuss linear combinations. Okay, when you have to add two normal distributions, okay, you can just add or subtract their means. But if you do the variance, remember it's always addition. Okay, you ignore if it's negative. Okay, because variance just talks about the distance. All right, so let's do an example. So here we have the radius of a wire, follows a normal distribution. It's then wrapped in a layer that follows another normal distribution. So now we want to know what the probability that the radius of the wrapped wire will have a total greatness than over 0.75. Okay, so first we need to find the new mean and the new variance. So we can start by doing that. The means, we just add those together. So the new wire, right, with both things, the original and the new thermoplastic layer. All right, and then the variance, you just add the two variances. All right, so now we have a normal distribution. And we want to know the probability that it's larger than 0.75. Pull out the calculator. Okay, so we use second VARs, normal CDF. We want to go from 0.75 to something large, 0.7, and then this one, remember, that's the variance. So we want to put in the square root, which is, the standard deviation, which is the square root. Ugh, I'm trying to do too much. We knock that out, and that gives us the percentage, the probability. So the probability that it's greater than 0.75 using a normal CDF function on your calculator. And that's all you got to do. All right, let's do another example. So here in example 2, we have two normal distributions, but then we want to do 3 times the first one and 2 times the second one, okay? And I want that probability to be greater than 30. So here we could start with the formula, all right? I know that might look a little confusing, all right? But it just follows the same rules. So since we're doing 3 times x and 2 times the second x, literally do that for your mean. So 3 times 3.5 plus 2 times 5. That gets you your mean. Then combine your variances. So 1.4 and 1.21. Now we know we're going to add them, but we're also multiplying by 3 and 2. Remember, with variance, you got to square it first. So you do that algebra, and you get this is your new mean, and this is your new variance. Okay, so now all you have to do is find the probability. So it should be 1.22%, rounded to 3 sig figs. Okay, so now that we did linear combinations with more than one random variable, let's go back to just focusing on only having one. So in this example, a farmer is selling peaches. You got the average rate, weight, and standard deviation. So he then fills them or puts them in boxes and transports them. Find the probability that a customer gets a box with more than this 3.9 or 0.96 kilograms of fruit. Okay, so now we've got to estimate the box, right? We've got a sample, just one sample based on that variable. Let's look at what we would expect on average on that customer's weight. Okay, so the minimum that the customer should get for each peach is that weight. Remember, it's kilograms, and this is in grams, so put that in grams. Divide by 18, we expect each peach to be 172 grams. Okay, now let's apply that to my new mean and standard deviation. Well, with my mean and my standard deviation, there is a change. Sorry, that was going to bother me. All right, so your mean stays at 175. We still expect each peach to be 175, but now that I'm selecting more of them, that variance between them gets smaller. So now I take my variance, remember the standard deviation is 5, so the variance is 25, and now I'm dividing by how many peaches I want, because the more peaches I choose, the less variance in my my sample, right? Because I expect them to follow that average more. Okay. The more peaches I collect, the better off that my average of those peaches will be the actual average of the population. Okay? So that's why my variance gets smaller with the more peaches I collect. All right? So now I've got this new mean and standard deviation. Now I want that probability to be greater than 172. Plug that into my calculator, normal CDF, and you get this. Okay? And that theory brings us to this central limit theorem. So that any random variable, all right, that sample mean is approximately normal, okay, if the sample size is large enough. Okay, so it doesn't matter what the distribution of that random variable is, all right? If I make it big enough sample size, okay, that mean and the variance will be below, that it can be distributed below, okay? All right, let's do an example. Okay, so for this example, we've got, we're taking, let's see, a sample population with mean of 27 and, population mean with 27 and standard deviation of 10. So what is the probability that it's between 25 and 29? So first, adjust your new mean. Oh, I went the wrong way. All right, first adjust your mean and your standard deviation. So your mean is still expected to be the same, even though I've collected now 45 data points. So I take my standard deviation, I square it to get the variance, and then I divide by 45. Using that, I find my probability with my normal CDF. All right. All right, so let's do example number 2. So using the same stuff from example 1, so mean of 27, standard deviation of 10, find the minimum n to guarantee that that probability is greater than 0.9. Okay, so, we could, all right, my first instinct was this. So I don't know if you guys remember, you have a inverse norm, right? Which sounds great because I know that the area is 0.9. I know that it's in the middle. Ooh, this one doesn't show it. If you have, let's see, the TI-84 plus CE edition, the one that I have at my personal one, not my computer one, it lets me pick either the left, center, or right. So I would pick the center. And then I would, because this is exactly in between, or 27 is in between that. And then your mean would be 27, but then we have an issue because we don't know what the standard deviation is, okay? Because we don't know what n is changing. So what we're going to do is we're actually going to graph this, okay? So maybe you're a visual person, so I'm going to show you what it is, the steps, okay? We're still doing that normal CDF, right? Where it's upper is 25, lower is 25, upper is 29, mean, but now the standard deviation has a variable. So we're going to plug the normal CDF into our line, okay, into our equation, and then we want it to be a probability of 0.9. So then we're going to graph those two lines and see where they intersect, because we know that this normal CDF, that output would give you the probability. So we want it to equal 0.9. So again, you go to y equals, this is from an old lesson. Okay, So we're going to go to second vars, normal CDF. We have lower, upper, mean, and standard deviation. And that's where we get our variable. So we pasted it there. The second line is the probability we want. And then I'm going to adjust my window. I know, let's see, x is our probability. So I know it's going to go from 0 to 1. I'll have that go 0.1. My minimum, oh wait, I'm sorry. Y, the output is the probability. So that one should go from 0 to 1 and then 0.1. The x is your n. So how many things do we have? Elements. So let's see. I think 100 is reasonable to start with, and if it doesn't get high enough, then we can adjust our window again. So now I can see the curve. Ooh, maybe I did too many data sets, but that's all right. It's going to take a second. It's almost to the end. There we go. There's 0.9, and then I can do my trace, second trace, and do the intersection and get right there. And that intersection happens when x is 67.6. So what do we say? Is x value going to be 67? Not quite, okay? Because we need, we know x has to be 67.638, blah, blah, blah. This is how many things, how many elements we need to get the probability to be 0.9. Well, I'm not going to have 67.6 things. And 67 things would get me less than 0.9%. So I'm going to round up and say 68 elements, okay? The minimum number of n, the number of samples, elements, whatever, x's, is 68 to guarantee a 0.9 probability. Now we notice for example 3, it's a binomial distribution. So we want to find the probability that Ronnie averages going to bed before midnight at least twice a week. So first we need to look at the expected value, or the expected and the variance. All right, so your new mean and variance. All right, back in, what was that, section 4.8? Okay, in case you forgot that. Let's see. Then we can plug that in into our mean and new standard deviation. So our mean is now 7/3, right? N times the number of weeks times the probability. All right, so this is what you get for the mean. And then our variance, all right, we're going to take our new variance and divide it by 52 because that's how many weeks there are in a year on average. Okay, so now we get this distribution. We want it to be more than 2, the average. Okay, so we plug that into our calculator for the normal CDF, and the probability that it's going to be greater than 2 is pretty good. All right, so this is all you need to know for section 15 and topic 4. If you have any questions, come see me in class.